Most maintenance jobs around the plant can be done using the right-hand tool and a little muscle. They're jobs that draw on the most basic maintenance skills, but they're often time-consuming and tedious. Many times the same job can be done more quickly and easily using the right power tool, in this case a power hacksaw. Power tools are not only quicker, they also give us an added measure of precision. You see, the mechanical muscles of a machine are usually much steadier than the muscles in an arm or a hand. Speed, strength, and precision. These are three of the biggest advantages of power tools over hand tools. Now, when you put power tools and hand tools side by side, you get the impression that the two groups are worlds apart. But, in fact, they're very similar. This bandsaw cuts with a flexible toothed blade, just as this handheld saw does. Now, this impact wrench uses sockets to turn nuts and bolts, just as this breaker bar does. And this power grinder uses an abrasive surface to remove metal, just as a grindstone does. Now, because these two groups of tools share the same basic purposes and functions, it shouldn't surprise you that the basic rules that apply to hand tools also apply to power tools. When you select a power tool, for example, you have to be sure to select the right one for the job. You have to inspect the tool carefully to be certain it's in usable condition. You need to wear the proper safety gear like goggles, face shields, and heavy long-sleeved shirts. And of course, when you're finished with any tool, it must be cleaned and stored properly so that it's in good condition the next time you need it. Although power tools and hand tools have much in common, power tools are, after all, far more powerful and complicated than hand tools are. It's one thing to make a mistake using a hand tool, but being careless with a power tool is an entirely different story. To ensure your safety and to protect your plant's investment in tools and equipment, there are certain precautions and procedures you must follow. First, secure your work before you start. Work that's not held firmly in place is liable to get thrown off the bench or table when it comes in contact with a power grinder, a saw, or a drill. Also, you can't accurately cut or grind something that shifts around. Second, protect yourself. Wear necessary safety gear. And check to be sure that all equipment shields, guards, and insulation required for your safety are in place. Third, inspect the tool carefully and know how to operate it. Know how to turn off the power quickly in case of an unexpected emergency. Remember, too, that many power tools generate sparks and frictional heat that can easily touch off fires. Make sure the area you're working in is fire safe before you start. In addition to the fire hazard, there's also the hazard presented by the cutting edges and rotating parts of the tools themselves. Don't put any part of your body in front of the business end of any power tool. Power tools can make short work of flesh and bone, and keep clothing, jewelry, and hair away from all rotating parts. A shirt tail or an unbuttoned sleeve can bring you and the tool together very fast. Finally, wherever you're working, whether in the shop or out in the plant, watch out for people around you. Be sure everyone is a safe distance away. Okay, that gives us some basic working rules for all power tools, but we haven't yet said anything about the power that drives these tools, compressed air and electricity. Now, pneumatic or air-driven power tools have air inlets. These inlets attach directly to hoses that carry air from an air source, such as a service air system or a compressed air container, to the driving mechanism inside the casing of the tool. Electric tools, on the other hand, have power cords that carry electric current from an outlet to the motor inside the casing of the tool. We'll save electric power tools for the next segment. Right now, let's look at some of the advantages and the hazards of using compressed air. The biggest single advantage of pneumatic tools is that they present no shock hazard. You can use them while standing on a metal deck or in 10 inches of water without worrying about electrocution. But that doesn't mean that pneumatic tools are worry-free. They can be dangerous. Just ask anyone who's been smacked senseless by a runaway air hose, or anyone who's had grit or metal chips blown into his eyes by someone horsing around or just being careless. So the first thing to remember is that compressed air can be dangerous when not properly handled. Now, before using any pneumatic tool, be certain it's properly matched to the air supply you're connecting it to. The pneumatic tools in your plant are probably matched to the service air system. This means that if the service air system is rated at 100 psi, the pneumatic tools in the plant will be rated at 100 psi or higher. But don't assume this is true. Know how much pressure the system in your plant delivers, and always check to be sure the tool you're using can handle the pressure. The nameplate on the tool will tell you the maximum pressure the tool can tolerate. Overpressurizing a pneumatic tool is a serious safety risk. Both you and the tool can be seriously hurt. Most compressed air accidents involve a malfunction of the hose that connects the tool to its air supply. So always inspect the entire length of hose before hooking it up. If you find one that's cracked or worn, don't use it. Check the connectors too. They should all be the same type and the same size so that they fit together properly. In many cases, the tools you're using will have a short length of hose called a pigtail already attached to the air inlet. If so, don't forget to check both the air inlet and its connector. Before connecting an air hose to a pneumatic tool, the hose must be connected to the air supply and tested. In this case, the hose is already attached to the service air system outlet, so after putting on eye protection, the mechanic inspects the connectors and checks the valve to make sure that the air is off. He then attaches an air nozzle, opens the valve, and shoots a few quick blasts of air through the hose to be certain it's clear of obstructions. Then he closes the valve and bleeds all remaining air out of the hose. Next, he disconnects the nozzle and sets it aside. He's now ready to connect the hose to the tool. Now, whenever two hoses are connected, or a hose is connected to a tool, a safety wire or spring-type safety connector like this one should be used to bridge the connection. Even if the connection fails, the safety connector will keep the hose from whipping around, causing serious injury. With all connections and safety wiring in place, he's ready to open the valve on the air outlet. He then puts on whatever additional safety gear is required. Finally, he gives the tool an operational test to be certain it's in working condition and begins work. While he works, he makes sure that the hose stays away from any moving parts. When he finishes the job, he sets the tool carefully on the table and shuts the service air system valve, cutting off the flow of air. Then he bleeds any remaining air out of the hose and the tool before disconnecting them and removing the safety connector. Before leaving the work area, he coils the hose neatly and stores it properly, making certain that the hose is away from water and dirt and out of the flow of traffic. Storing your air hoses properly increases the life of the hoses. A hose that's stored with kinks in it will weaken. A hose left in water or dirt may clog and require cleaning out before its next use. In this segment, we've covered some of the basic rules for working with all types of power tools. We've also seen precautions and procedures that apply to pneumatic tools in particular. So that you're sure to understand everything we've seen so far, turn off the tape and review segment 1 of your text. Then, in the next segment, we'll look at the second major category of power tools, electric power tools. Electricity is something we all use every day. The lights and the appliances you use at home, even the television you're watching now, all run on electricity. And because electricity is so much a part of our lives, we often take it for granted. We get careless, we take shortcuts, we ignore safety precautions, and the next thing we know, we're waking up on the other side of the room. But there are hundreds of people every year who don't wake up after electrical accidents. Electricity can be a killer, and we're inviting it to kill whenever we allow it to get out of our control. While electricity is familiar to all of us, it's still a very complicated subject. I think we can simplify it somewhat, though, by studying this graphic, which shows a mechanic holding a portable electric drill. The power cord of the drill is plugged into an electrical outlet, which in turn is connected to a source of electricity. If we take a look at a cutaway section of the power cord, we see two conductors, each one wrapped in its own insulation. The conductors provide a path for electric current to flow through. The insulation prevents the current from escaping from the conductors. To prevent damage to the insulation on the conductors, both insulated conductors are covered by another sheath of insulation. When the mechanic turns the drill on, current flows from the outlet through one of the conductors and into the drill. The current then returns to the source through the second conductor. This continuous path from the source to the tool and back to the source is called a circuit. As long as the circuit remains intact, the drill operates properly. But the circuit may not remain intact. Let's go back to the cutaway of the power cord. If the insulation in the power cord fails and the two conductors are exposed to one another, current flows directly from one conductor to the other. The result is a short circuit. Instead of following the full circuit, current flows only up to the break before going back to the source, and the buildup of current at the short circuit can literally burn the cord. For this reason, it's important to inspect power cords and extension cords carefully. Make sure there are no cuts or breaks in the insulation. And to protect power cords and extensions, avoid laying them near heat sources, rotating machinery, or traffic lanes, all of which can burn or cut the cords, causing a short circuit. A short circuit isn't the only malfunction that presents a hazard. Another common malfunction is called a ground short, or simply a ground. A ground short occurs inside the tool when the current, instead of flowing along its normal path, flows into the metal parts and casing of the tool. A ground short is just what its name implies. It's the current finding its own path into the ground and back to its source. Since the human body is a fairly good conductor, it gives the current just the path it needs to get into the ground. The mechanic literally becomes part of the circuit, and the electricity could electrocute him. And let me try to clear up one common misconception here. You don't actually have to be standing on the ground to be in contact with the ground. If you're standing on a metal deck, a raised metal platform, or even a concrete floor, you're still connected to the ground. You're still grounded, and you still run the risk of electrocution if a ground short occurs. To protect electric power tool users when ground shorts occur, manufacturers incorporate one of two safety features into their tool designs. The first is the addition of a ground pin to the plug and a ground conductor to the power cord. Now, what the ground conductor and pin do is connect the tool casing directly to the ground. Current flows more readily through the ground conductor than through the human body, so when a ground short occurs, current flows through the ground conductor instead of through your body. Plugs with ground pins are called grounded plugs, and they fit only in outlets that have a ground connection. A third hole, like the one you see here. This hole is connected directly to the ground. You can see that the grounding feature in a power tool is very important, but like any other safety feature, it works only if it's in good condition. So, if the plug on the tool you're using is supposed to have a ground pin, but the ground pin is missing like it is on this plug, don't use the tool. And don't make the mistake of plugging a 3-prong plug into a 2-prong extension cord. A connection like this is useless and dangerous because the ground wire isn't connected to anything. Now that tells us about the safety ground feature in an electric tool like this one. But this electric tool is different. It doesn't have a ground pin, and its casing is plastic instead of metal. This is a double insulated electric drill. It has the same motor and wiring insulation that other electric tools have, but the tool casing is made of plastic, which is an insulating material. So, even if an electrical malfunction occurs inside this tool, the plastic casing protects you from shock. It therefore needs no ground conductor. Of course, double insulated tools, like safety grounded tools, work only if they're in good condition. Don't use a double insulated electric power tool if the outside insulation is cracked or otherwise damaged. And be careful when handling a double insulated power tool. The plastic casing is not as strong as a metal casing and can crack rather easily. We spent a lot of time discussing electricity and electrical safety, and as we look at individual electric power tools, we'll go into more detail about safety procedures regarding their use. But right now, turn off the tape and read section 2 of your text. Few power tools get more use or do more jobs than the portable grinder. Equip it with a grinding disc, and it'll remove metal quickly and easily from large or flat stock. Attach a grinding wheel, and you have a tool that can form bevels and do irregular shaping. A special cut-off wheel turns a portable grinder into a tool that can cut a window in a boiler tube. And a wire wheel can be used to remove slag from welds and corrosion from almost any metal surface. To handle such a wide range of jobs, portable grinders come in a variety of sizes and shapes. 3 of the most common types are the side grinder, the largest of the 3, with its shaft mounted on the side of the casing. The pencil grinder, slightly smaller, with its shaft at the front of the tool. And the small high-speed grinder. As a general rule, the larger the grinder, the slower its rotational speed, and this is because larger grinders turn larger wheels and are designed for heavier jobs than small grinders. So larger grinders need power more than speed. To find out what the speed of a particular grinder is, look here on the nameplate of the tool. You'll find the rotational speed stamped right on it. If the nameplate is missing, don't use the tool. Guessing at the speed of a portable grinder could lead to injury. With an assortment of portable grinders to choose from, how do you know which one to use? Well, it depends on the job you're doing and the type of wheel you need. If you have to do a lot of heavy grinding, you'll want to use a large, heavy-duty disc. And to drive that disc, you need a powerful grinder, like this side grinder. Now, for cutting a sleeve off a shaft, a large cut-off wheel and grinder might be too awkward and too hard to control. So you'd likely use a small cut-off wheel and choose a pencil grinder to drive it. And where precision shaping of thin metal is essential, you'd probably choose a cutting element like this one. This is a rotary file, often called a burr. A burr is made of very hard metal, and its surface is covered with sharp cutting edges. It's built to tolerate high rotational speeds, and it's used with a high-speed grinder. So, selecting the right grinder depends in part on selecting the right attachment. And to help you select the right attachment, all wheels, discs, and burrs for portable grinders are stamped or otherwise labeled with two important bits of information: the manufacturer's code and the speed rating. This grinding wheel, for example, has the manufacturer's information printed right on it. The code of letters and numbers gives you the information you need to properly match the wheel to the type of metal you're working with. Your text gives details on how to read this code so you can select the right wheel for the job. The other thing we're interested in is the speed rating of the wheel, the maximum number of RPM that the wheel can safely turn at. This wheel is rated for 7,750 RPM. Now, to keep below this maximum, the grinder you use to drive the wheel must rotate slower than 7,750 RPM. Using a wheel on a grinder that rotates too fast pushes the wheel beyond its limit. The wheel could easily shatter and cause serious injury to you and anybody working around you. So when you've selected a wheel for a job, the first thing to do is to make sure the speed rating of the wheel is higher than the speed of the grinder. Now, the procedure for attaching a wheel to a grinder varies from grinder to grinder. In the case of this side grinder, the wheel is simply turned onto the threads of the shaft. Then, a pair of wrenches is used to tighten the wheel. On this particular grinder, a spanner wrench is used to hold the shaft nut, while an open-end wrench is used to tighten the wheel. Now, since this is a pneumatic grinder, it must be connected to an air supply. First, however, check the hose by giving it a short blast of air to make sure it's not obstructed. Then close the valve and bleed the remaining air out of the hose. Next, remove the air gun and connect the hose to the tool. Notice that a safety wire is used to bridge the connection. It's important that the power switch on the tool is in the off position while the hose is being connected. Otherwise, when you turn the air on, you run the risk of the tool starting up and leaping off the table at you. When the grinder is properly connected, go ahead and turn on the air. And remember to test the grinder before you bring it in contact with the work. When you're using a grinding disc, be sure to hold the flat surface of the disc against the work, and exert only enough downward pressure to keep the wheel in contact with the metal. Using the edge of the disc or pressing down too hard on the grinder can shatter the disc and injure you. Whenever you're grinding, be certain that there's no one nearby who can be hit with a stream of sparks. Also, try to direct any sparks or metal chips downward where they'll be less likely to cause injury. Now, installing or changing a wheel on a pencil grinder like this one is a little different than on a side grinder. Here, the wheel is held in place by a lock nut and washer. They must be removed before the wheel will come off the shaft. The replacement wheel is slipped onto the shaft, and the washer and the lock nut are replaced. To evenly distribute the pressure from the lock nut, it's important that the washers seat properly against the wheel. Also, the lock nut must be tightened enough to prevent the wheel from slipping or working loose. Before connecting the air hose, be certain the power switch or lever is in the off position. Because this air hose was just checked, there's no need to test it again before connecting it to the tool. When the connection's been made and checked, the air valve is opened, and gloves and a full face shield are put on. Finally, when you've given the grinder an operational test, you're ready to go. Unlike a grinding disc, a wire wheel is designed to be used edge-on against the work. But use only enough downward pressure to keep the wheel against the metal. Too much pressure can damage the wheel. When you're done grinding, of course, you have to turn off the air supply. After turning off the air, turn the grinder on to bleed any remaining air out of the system. And wait for the wheel to stop turning before disconnecting the hose. When you're doing a job that requires a high-speed grinder, there's a special procedure for installing and changing out burrs. This is because each burr is permanently attached to its own shaft. This shaft fits into a chuck on the end of the grinder. Of course, the burr you select must be inspected. To cut properly and safely, its shaft must be straight and all its cutting edges intact. If the burr is in good shape, insert it as far as it'll go into the chuck and hand tighten the chuck collar. To lock the burr in place, use one wrench to keep the chuck from turning and another to tighten the collar. Next, follow plant procedures for hooking up the air hose and opening the air outlet. When using a high-speed grinder and burr, follow the same general guidelines that you do when using other portable grinders. First, allow only the cutting surface of the burr to touch the work. With this cone-shaped burr called a Christmas tree, the cutting edges are along the tapered surfaces. And don't be in a hurry. High-speed grinders are built for precision. They're not fast-cutting tools. Don't try to make them cut faster by exerting excessive downward pressure. If you want to do the job faster, use a different grinder. As we've seen, portable grinders aren't difficult to use, but because they can do so many different jobs, there's a lot to know about them. So, right now, read through section 3 of your text. Then have your instructor show you some of the different types of grinders used in your plant and the kinds of jobs they can do. Sawing metals by hand is one of the most time-consuming and energy-consuming jobs in the plant. And the result is often an uneven cut, because sawing accurately by hand depends largely on the mechanic's stamina and his ability to make every stroke exactly the same. A power hacksaw eliminates this problem. Its built-in vise holds the work steady, and its replaceable blade is mounted on a mechanical arm that can cut faster and more accurately than all but the most skilled mechanic. A control rod is used to hold the blade arm in its lowered position or to release it. And power switches or buttons are provided to turn the saw on and off. Remember, the accuracy of the final product depends on the accuracy of your planning, so be certain that the work is properly laid out before starting. To align the saw blade with a layout line, engage the control rod, and then lower the blade until it's just above the work and reposition the work if necessary. When you're sure the alignment is right, tighten the vise securely around the work. Then, make sure your eyes are protected and lubricate the blade to cut down on frictional heat. And finally, start the saw. In addition to moving back and forth, the arm and blade also move downward on each stroke. A blade pressure control on the machine allows you to adjust the downward force of the blade. For hard metals, blade pressure should be light to prevent the blade from overheating and breaking. For soft metals, blade pressure can be increased, since soft metals can be cut more quickly without damaging the blade. Whatever pressure setting you use, though, you can't ignore proper lubrication. Many power hacksaws have automatic lubrication systems that cool both the blade and the work with a constant flow of lubricant. On other types, lubrication must be applied by hand. In either case, use only lubricants recommended by the tool manufacturer and suited to the type of metal being cut. And make sure lubrication is supplied constantly to minimize frictional heat that can damage the blade. Of course, whenever lubricating by hand, keep clear of all moving parts. When the blade is cut completely through the work, switch the power off, but wait for the blade to stop moving before releasing the control rod and raising the arm out of the way. And when you do remove the work, remove the waste metal also. This way, the hacksaw will be cleared off and ready for the next person to use. The power hacksaw is ideal for making straight cuts in pipe and thick stock. But it's useless for cutting irregular shapes like the one laid out here. A good tool for doing irregular cutting is the vertical bandsaw. Bandsaws differ in their size and design, but they're basically made up of a blade guard, a table for supporting the work, and various controls. A look inside this bandsaw shows that the blade is a continuous loop that rotates on two large wheels. When the casing is closed, only a small section of the blade is exposed. The blade guard controls how much of the blade is exposed at a particular time. One control knob locks or unlocks the blade guard. A second knob raises and lowers the guard. This particular bandsaw has 3 gear ranges. A pair of gear levers is used to change from one speed range to another. For a particular job, the speed of the blade is further set within a given range using the blade speed control. The speed of the blade registers on a blade speed gauge. The exact speed to use is based on the blade being used and the size and type of metal being cut. Typically, the power switch of a vertical bandsaw has 3 positions: safe, which is the off position; jog, in which the motor runs only as long as the switch is held in that position; and run, in which the motor runs continuously until the switch is moved to the safe position. A stop button is provided for emergency situations. Because a vertical bandsaw is such a powerful and potentially hazardous power tool, it's essential that you learn to operate it properly. The first step is to be certain the power switch is in the safe or off position. You can then unlock and lower the blade guard so that the work will just pass under it. Getting the guard as close to the work as possible has 2 advantages. It keeps the blade taut, eliminating blade wobble during cutting, and it reduces the length of blade that's exposed, thereby minimizing the safety hazard to the operator. When the guard is locked into place, consult the manufacturer's guide to find the right gear range and blade speed for the blade you're using and the metal you're cutting. Make sure the gears are properly set. Then turn the power knob to the run position, since blade speed can only be adjusted when the blade is rotating. Using the speed control, adjust the speed of the blade. There is a blade speed gauge that will help you tell when the speed is set correctly. Finally, you're ready to cut the metal. Put on a full face shield and begin to guide the metal against the blade. The important thing to remember here is to keep your hands and arms away from the blade. Be certain your shirt cuffs are buttoned and your shirt tail is tucked in. And if your hand has to work this close to the blade, it's best not to wear gloves. They could get caught in the blade. A good safety practice is to use a wood pushing block to guide the last few inches of the work against the blade. That way, when the blade reaches the end of the work, the wood, rather than your fingers, will be the last thing to hit the blade. When you finish cutting, turn off the saw and remove the work from the table. But don't put your hands anywhere near the blade until it has stopped moving. When the blade is stopped, unlock the blade guard and raise it out of the way so that you have room to sweep the metal chips off the table. As with the other tools we've seen, good housekeeping keeps the tool clear of debris and ready for the next guy to use. Now, the vertical bandsaw is fine for work you can bring into the shop and set on the table. But for jobs that you can't bring into the shop, you need a different type of bandsaw. This is a portable bandsaw. Like its big brother, it also has a continuous rotating blade that can cut very, very fast. But there's an added danger here. A portable bandsaw is pretty heavy and not always easy to control, especially when you're using one for the first time. And if you're making a cut above shoulder level or in a tight spot, it can easily slip and give you big problems. So whenever possible, avoid situations where you have to stand under or close to the blade of a portable bandsaw. Now, another portable saw intended for heavy-duty service is the reciprocating saw. The reciprocating saw gets its name from the fact that its straight, hardened blade cuts with a reciprocating or back-and-forth motion, much like the motion of the power hacksaw. The reciprocating saw doesn't cut as fast as a bandsaw does, but one advantage of a reciprocating saw is that its blade extends straight out of the front. This enables it to reach into tight places, and it also puts a good bit of distance between you and the blade. Now, a reciprocating saw usually comes with its own rigging. The rigging is an optional feature, and you don't have to use it. But when properly used, the rigging holds the saw steady against the work, giving you excellent control and allowing you to make even, accurate cuts. All of the power tools we've seen in this segment are powerful and relatively fast cutting. And the most important rule to follow when using them is safety first. Being careless for only a blink of an eye can cripple you for life. So as you read through segment 4 of your text, keep safety in mind. And make sure the safety rules you learn today stay with you when you leave the classroom and go out on the job. Many of the jobs you'll do involve threaded fasteners, and not just one or two fasteners, but several or even dozens. Tightening or removing a series of nuts or bolts can be tedious if you have to do it by hand. But an impact wrench like this pneumatic one makes the job a lot easier. An impact wrench is basically a power socket wrench. Special impact sockets fit on the drive lug of the wrench. Different size fasteners, of course, require different size sockets. In this case, an extension must be used to provide necessary clearance between the tool and the valve casing. On this particular impact wrench, a metal pin slipped into matching holes in the extension and the drive lug holds the extension in place. Then a rubber ring covers the holes to prevent the pin from slipping out. The impact socket attaches to the drive lug of the extension in the same way. The hole in the socket is lined up with the hole in the extension. The metal pin is slipped into place. Then the rubber ring is positioned to keep the pin from flying out when the wrench is turned on. While the mechanic hooks up his air supply and hoses, let's take a moment to look at sockets. Here we see two sockets. The one on the left is the type of socket used on handheld socket wrenches. The socket on the right is an impact socket. Notice that the walls of the impact socket are much thicker than the walls of the ordinary socket. Impact sockets are built this way to handle the stress exerted by the impact wrench. If you accidentally put an ordinary socket on an impact wrench, you'll end up with a couple of ounces of flying shrapnel. Another type of impact socket you should know about is the splined impact socket. The splines in the drive end of the socket mate with the splines on the drive lug of the tool. Most very large or heavy-duty impact wrenches have spline drives because they can withstand greater stress than square drives can. Okay, as we rejoin our mechanic now, he's already connected the impact wrench to its air supply. He just opened the valve at the air outlet, so he's about ready to start tightening the casing nuts. First, of course, he puts on his safety gear. Then he tests the controls. The back of the casing is actually a knob that controls the direction that the wrench turns. He makes certain it's set to tighten the nut. And when he places the socket on a fastener, he holds the wrench straight and ensures that the socket fits squarely on the fastener. When the fastener is tight, the clutch inside the tool slips and prevents the wrench from over-tightening the nut and possibly ruining the threads. So when he hears the clutch slip, the mechanic releases the trigger and waits for the motor to stop before removing the socket from the fastener. As you can see, an impact wrench makes quick work of the series of fasteners. Of course, not all the fasteners you'll come across will be the same size or type. As far as size is concerned, most fasteners can be tightened or loosened with a handheld impact wrench, like this one or the one we demonstrated earlier. But when you're working with something the size of this turbine casing bolt, a small impact wrench can't do the trick. That's when you need a really large impact wrench, like this 1.5-inch drive model. An impact wrench this big takes 2 people to handle it safely. And the noise it generates is loud enough to cause permanent hearing loss. So be certain to wear proper ear protection. In the course of your career, you're likely to see dozens of different types of impact wrenches. By and large, though, they all operate in just about the same way. So, if you're careful to select the right one and equip it with the right impact socket, you shouldn't have any trouble using it safely. There's another power tool I'd like to show you in this segment. It isn't related to impact wrenches, but like the impact wrench, it can save you a lot of time and energy on the job. This is the tool, a pipe threading machine. The pipe threading machine is basically a power chuck and a set of cutting tools. The machine can be mounted on a portable cart or bolted to a bench or a table. 2 of the 3 cutting tools, a pipe cutter and a reamer, are permanently mounted on the machine. There's also a lubrication arm here that automatically provides lubricant during all cutting operations. The reamer, pipe cutter, and lubrication arm are mounted on a carriage that's moved back and forth by means of a hand crank. The 3rd cutting tool is a removable, adjustable die stock with pipe dies. Many pipe threading machines also have a foot pedal that allows a mechanic to operate the machine while still keeping both hands free. The foot pedal only works when the power switch has already been turned on. When using the pipe threader, first make sure the power switch is off. Then slip the pipe into the chuck and lock it into position. The pipe should stick far enough out of the chuck on the tool side so as to give the tools plenty of room. This pipe is already cut to length, so the pipe cutter will not be used. But cutting the pipe left a burr along the inside lip. If this burr is not removed, it could break loose when the pipe is installed, fouling the system the pipe is part of. To remove the burr, the mechanic swings the reamer in line with the pipe and adjusts it to its forward position. He cranks the reamer almost in contact with the pipe and lowers the lubrication arm. When the chuck begins to turn, lubrication flows automatically, keeping the reamer and pipe cool. The mechanic uses the crank to guide the reamer just far enough into the pipe to cut off the burr. He then stops the chuck and moves the reamer and the lubrication arm out of the way. Next, the mechanic must select the proper die stock and pipe dies. The die stock is nothing more than an adjustable holder for the dies, which fit into the 4 numbered slots in the stock. Because the mechanic is using this die stock on 1.5-inch pipe, he has properly set it for 1.5 inches. With the dies properly installed and the die stock adjusted, the mechanic mounts the assembly on the carriage and positions it near the end of the pipe. Then he swings the lubrication arm into position and starts the chuck. When the chuck begins to turn, he cranks the dies into contact with the pipe. As soon as the cutting edges of the dies engage the pipe, he lets go of the crank. Once the die begins cutting, they automatically feed onto the pipe. Now, how does he know when enough threads have been cut? Well, the correct number of threads has been cut when all the cutting edges of each die are in contact with the pipe. That is, when the trailing ends of the dies are flush with the end of the pipe. At that point, open the die stock to move the dies away from the pipe. Then, stop the chuck and crank the die stock out of the way. After inspecting the threads to be certain they're all right, remove the die stock from its mounting and clean it. A small brush is best for cleaning metal shavings from the cutting edges of the dies. And a clean rag should be used to wipe excess lubrication off the die stock. Then return the assembly to its shelf and remove the pipe from the chuck, being careful not to damage the new threads as you do so. When used properly, the pipe threading machine is among the most practical tools in the plant. You can learn more about it by reading Section 5 of your text. Drilling holes is among the most basic metal cutting operations. You can't use studs, bolts, or pins without drilling holes to put them in. You can't pass a wire through a wall or a pipe through a plate without first drilling a hole. For many drilling jobs, absolute precision isn't necessary, so a handheld portable power drill is all you need. Where precision is required, you need a drill press to accurately control the angle of attack, the speed of the cut, and the depth of the hole. But whether you use a drill press or a portable power drill, the heart of any drilling procedure is the twist drill itself. A twist drill, or drill bit as it's called, is a length of round steel stock with a fluted section, called the body, and a shank that's made to be inserted into the chuck or spindle of a power drill or drill press. The fluted body ends in a point, where the flutes form a pair of cutting edges called lips. This is also the widest part of the twist drill and ensures that the hole being drilled will be slightly larger than the diameter of the body, thereby preventing the drill's binding in the hole. There are two basic categories of twist drills, those with straight shanks used in portable power drills and small drill presses, and tapered shank twist drills designed for use in large drill presses. Both types are available in a wide range of sizes to meet almost every drilling requirement. But because this segment deals only with portable power drills and small drill presses, the twist drills we'll see are all straight shank twist drills. The best way to learn about twist drills is to watch one being used properly. The mechanic starts by securing the work in a vise so that it can't shift around during drilling. Because precision isn't critical for this job, a portable power drill is a practical choice because of its ease of operation. It consists basically of a motor inside a pistol grip casing with a trigger powering switch and a chuck for holding the twist drill. Before any power drill is used, it must be inspected. The chuck should function properly. So should the power trigger. Because this is an electric power drill, the mechanic is careful to include a thorough inspection of the power cord and the plug in his preparations. He then inspects the twist drill he's going to use. He makes sure the shank is straight and that the cutting edges are sharp and intact. Satisfied that the equipment is in good condition, he opens the jaws of the chuck by turning the chuck collar and then inserts the shank of the drill bit as far into the chuck as it will go. He uses a chuck key to tighten the chuck so that the twist drill won't slip or come loose. A chuck key is a small toothed device with a bar handle. It's usually attached to the power cord near the plug. It's put there for a reason, to ensure that the tool is unplugged whenever the chuck key is used. The end of the key fits into a hole in the side of the chuck and engages matching teeth in the chuck collar. And since the mechanic is going to have to use an extension cord, he inspects both the plugs and the entire cord for wear or damage. Finding the extension cord in good shape, he can connect it to the power cord of the drill. Notice that he ties the power cord and extension cord together to prevent the connection from pulling apart during drilling. He can then plug the extension cord into the outlet and put on his safety gear. Notice that he's center punched the aluminum plate exactly where the holes are to be drilled. These punch marks not only mark the location of the holes, they also provide a starting point for the drill to get a good bite into the metal. Before drilling, he gives the drill an operational test. Now, the most important thing about drilling with a portable power drill is to keep the drill bit at the correct angle. If the hole is to be drilled straight into the work, the drill and drill bit must be held so that the drill bit is at a right angle to the surface of the work. With experience, you'll learn to exert enough pressure to do the cutting, but not so much that you overheat the twist drill. You'll find that more pressure can be exerted when a soft metal like aluminum is being drilled than when steel or other hard metal is being cut. And ease up as the drill is about to penetrate the work. Otherwise, you're likely to lose your balance and fall against the work. You could be injured and the drill bit is likely to get damaged. You'll also have to be careful when removing the drill bit from the chuck. Drill bits get hot from friction, and if you grab the bit right after drilling a hole, you'll end up with a painful burn. So far, we've seen how a twist drill is used in a portable power drill. But what about using a twist drill in a drill press? Well, let's start with the drill press itself. What you see here is a fairly typical upright drill press that stands on the floor. It has a table that can be adjusted up or down or tilted from side to side, and a part called a head that includes the motor and controls. But an upright drill press is not the only type. This is a bench drill press. It's designed to be mounted on a workbench or work table, so it has no table or base. This is a large radial drill press. It's much larger and heavier than the other drill presses we've seen, and it can handle cutting jobs with a precision that smaller drill presses can't match. In addition, many of the controls and features that are manual on smaller drill presses are automatic on this one. But for normal day-to-day jobs, an upright drill press is satisfactory. So let's spend a few minutes looking at its major parts and controls. The parts of the drill press that do the work are the spindle and the chuck. These parts rotate to turn the drill bit. The spindle and chuck are raised and lowered by turning a spindle feed handle. Feed is a term used to express the rate at which the spindle moves downward and therefore how fast the drill bit penetrates the work. Another important control is the adjustable depth stop. The depth stop is used to limit the distance that the spindle and chuck can be lowered. It consists of a nut on a threaded scale. The spindle can move downward only until the nut hits the stopping point. And the lower you set the nut, the less distance the spindle can move. Finally, there's the spindle speed or drill speed control. This control regulates the rotational speed of the drill bit. The speed control on this particular drill press is a wheel. Other drill presses can have different types of speed controls. As you learned from your text, different metals require different drill speeds. On most drill presses, the speed control can be adjusted only when the spindle is turning. One of the best ways to demonstrate the advantages of a drill press is through a procedure known as three-stage drilling. As its name implies, the procedure involves drilling in 3 steps. First, a small tapered twist drill called a pilot or starting drill is used to cut a narrow hole in the work. Now, this does 2 things. First, it gives the larger twist drill a guide hole to follow. Secondly, it removes some of the metal so that the larger twist drill will have less metal to cut and will therefore last longer. Then, the twist drill is used to cut the hole to within about 1/32 of an inch of its intended diameter. Finally, a reamer is used to enlarge the hole to its intended diameter and to accurately smooth the hole. Now, unlike a twist drill, which is wide at the point but narrower behind, a reamer has the same diameter along its entire length. As a result, there's no play between the flutes of the reamer and the walls of the hole. The walls of the hole keep the reamer steady as it cuts, preventing the wobbling that occurs when a twist drill cuts. So when you need a hole that's perfectly round, the final stage in drilling the hole should be to use a reamer. Now, we've talked a little about the controls and functions of a drill press and the procedure for 3-stage drilling. Now let's watch a demonstration. Here the mechanic is preparing to drill a hole in a pair of matching plates. The hole must be precisely the right size so that an alignment pin can be inserted through the plates. For the hole to be accurate, the layout must be accurate, so he measures carefully and marks the work accordingly. He then puts on his eye protection and center punches the work at the spot where the hole is to be drilled. Center punching is just as important here as it is when using a portable power drill. With the work laid out the way he wants it, he's ready to set up the drill press. He's using a pair of C-clamps to hold the work in place. Another type of clamp could be used as long as it held the work securely. Before tightening the clamps, though, he has to make sure that the center punch mark lines up with the spindle, the chuck, and the hole in the drill press table. And to do that, he uses a center finder. A center finder is a cylindrical length of metal with a pointed tip used to align the chuck and spindle with the work. After locking the center finder, he lowers the spindle until the center finder is just above the work. This may require adjusting the depth stop. The spindle is locked into position with the spindle locking lever. The center finder allows him to adjust the position of the work to ensure that the drill will hit right on target. When the clamps have been fully tightened, he releases the spindle lock and raises the spindle back to its highest position. He then removes the center finder from the chuck and replaces it with a starting or pilot drill. Two things are to be remembered when using a pilot drill. One is that because the spindle exerts so much downward pressure on the work, lubrication is required to keep the drill cool. The second is that the drill speed must be properly set for the metal being cut. Again, you'll have to adjust the depth stop. The pilot drill doesn't have to penetrate all the way through the work. It must penetrate only deep enough to guide the larger twist drill later on. When the pilot hole is drilled, the mechanic turns off the drill press and waits for the spindle to stop turning before removing the drill bit. And now he's ready for the larger twist drill. After locking the twist drill into place, he turns on the drill press and adjusts the drill speed to a slower rate. The twist drill is larger than the pilot drill and so requires less speed and more power to cut. Again, lubrication is important to keep the twist drill from overheating. The rate of feed is important too. The spindle should be lowered fast enough to keep the drill cutting, but not so fast as to overheat and damage the drill. When the twist drill penetrates all the way through the work, he raises the spindle and turns off the drill press. While he waits for the spindle to stop turning, he cleans the metal shavings off the work so that none of them get in the way of the reamer. Finally, he's ready for the reamer. Before installing it, though, he carefully inspects it to be certain its cutting edges are intact. Of the three cutting tools used in three-stage drilling, the reamer requires the slowest drill speed. It still requires lubrication, though, to keep it cool. Because a reamer is usually more fragile than the twist drill, particular care must be taken not to feed the reamer too quickly into the work. When the reamer passes through the work, the mechanic again raises the spindle and turns off the drill press. After the reamer stops rotating, he removes it from the chuck and sets it aside. He also removes the work from the drill press table. And uses a clean rag to wipe off the metal shavings and excess oil. And before returning them to storage, he cleans metal shavings and excess lubricant off the three cutting tools he's used. As with the other power tools we've seen in this unit, the drill press isn't difficult to use, but there are specific procedures and precautions you have to follow to protect yourself and the machine. A lot of what you have to know will come with the practice and experience. But no matter how experienced you become, don't take shortcuts with power tools. A power tool is as dangerous in the hands of an overconfident operator as it is in the hands of a novice. So no matter how skilled you become in the use of the power tools we've seen, and the dozens of different ones you'll come across in your career, remember that safety comes first.